The next principle which we are going to discuss is the Pauli Exclusion Principle. According to this principle, that no two electron in an atom have the same value of the 4 quantum number. That means, for example, if I'm writing the electronic configuration of the beryllium, whose atomic number is 4, that is 1s2, 2s2 and 2s2 ना. अब देखिए, अगर हम इन इलेक्ट्रॉन की, इसमें से एक इलेक्ट्रॉन की मैं बात करूं, तो अगर एक इलेक्ट्रॉन की अगर मैं बात करूं, तो इसका प्रिंसिपल क्वांटम नंबर n क्या है, दैट इज 2. इसका ऑर्बिटल क्या है, दैट इज अजमेथल क्वांटम नंबर, दैट इज s. अब s की अरेंजमेंट एक ही होती है, वो आगे पीछे जो है वो मूव नहीं करता, तो उसका मैग्नेटिक भी क्या रहेगा, सेम रहेगा. इसका मतलब है इसका एज प्रिंसिपल, एजमेथल, मैग्नेटिक क्वांटम नंबर ऑल आर सेम ना. बट और ये सिर्फ एक इलेक्ट्रॉन का नहीं है, दूसरे इलेक्ट्रॉन की भी ये सारी कैरेक्टरिस्टिक्स जो है वो सेम है. Having same principal number, quantum number, azimuthal quantum number, magnetic quantum number, then that means its fourth quantum number, that is called as spin quantum number, is different. That means if one of the electron 2s में है ना, तो that is like this. तो अगर इसकी एक आपका जो है वो इस डायरेक्शन में होगा, तो दूसरा आपका डाउनवर्ड में डायरेक्शन में होगा. इसकी स्पिन क्वांटम नंबर अगर +1/2 होगा, इसका हमारे पास होगा -1/2. So that means no two electron in atom have the same value of 4 quantum number. If they have 3 same quantum number, then the fourth spin quantum number must be different. ठीक है. So if two electrons which are present in the same orbital, the two electron can occupy the same orbital only if they have the opposite spins. For example, if we're talking about we can take the example of the oxygen, whose atomic number is 8, 1s2, 2s2, 2p4. ओके. अगर हम p शेल की बात करें, 1 2 3 4, और if we're talking about these two electrons, आपको ये हमारे पास, this is px, this is py, this is pc. ठीक है. अगर हम बात करें इसके प्रिंसिपल क्वांटम नंबर की n, that is 2. अगर हम इसके एजमेथल क्वांटम नंबर की बात करें, दैट इज p. अगर हम इसके मैग्नेटिक क्वांटम नंबर की बात करें, तो दैट इज px. दैट मीन ऑल दीज 3 quantum numbers are same ना. These 3 quantum numbers are same for first electron as well as for second electron ना. इस इलेक्ट्रॉन के भी तीनों क्वांटम नंबर्स यही हैं, और इस के भी तीनों क्वांटम नंबर जो है वो यही हैं. लेकिन इसका जो स्पिन क्वांटम नंबर होगा वो होगा +1/2, और इसका जो स्पिन क्वांटम नंबर होगा दैट is equals to -1/2. So that means according to this principle, if अब अगर हम इनकी बात करें, तो ये तो केस से डिफरेंट है ना, क्योंकि तो इनके तो प्रिंसिपल क्वांटम नंबर ही डिफरेंट है. Pauli's exclusion principle is basically based upon the electrons which are present in the same orbital. If they are present in the same orbital, then it is really very understood that they have the same principal quantum number, they have the same azimuthal quantum number, they have the same magnetic quantum number. All these 3 quantum numbers are same. The only difference can lies in the fourth quantum number, that is the spin quantum number. ठीक है. और अगर ये जो इलेक्ट्रॉन्स हैं px के, अगर हम इसको यूं अलाइन कर देंगे, तो that is totally wrong. Why wrong? Because then they have the all 4 same quantum number. So that's why the electrons which are present in the same orbital can have the opposite spin. Where we can discuss many other example. For example, nitrogen 7, whose atomic number is 1s2, 2s2, 2p, 5. No, it's not 5. Then we will 2p3, 1s2, 2s2, 2p3. Here you can look at these two electrons have 3 same quantum numbers, but fourth one is different because it may have +1/2 and it may have -1/2. 2. And here you can see they have the same spin. That means its spin quantum number may be have plus 1 by 2, but in case the principal quantum number and they are also same, that is 2, that is 2, और इसका जो azimuthal quantum number है that is also same, that is p, but its principal its as magnetic quantum number is different. Here it is maybe pxy, this is pz, this is py. So basically they have the different orbitals, but the electron which are present in the same orbital have the different spin quantum number. It's one of the direction is plus 1 by 2 while the other direction is minus 1 by 2. Here you can see this is an example of the oxygen. Oxygen atomic number is 8, 1s2, 2s2, 2p4. Here you can see this is called as 2px, have the same principal number, that is quantum number 2. Azimuthal quantum number is p, that is basically indicate 1. Px same azimuthal quantum magnetic quantum number, but this have the different, this is plus 1 by 2 and this is minus 1 by 2. Same is the case with these one and these one. Here the example of the fluorine. Here you can see in the fluorine these orbital electrons have this lie in the same orbital having 3 same quantum numbers, but its fourth quantum number, that is spin quantum number, that is different. These are 2 electrons. So basically Pauli's exclusion principle can help us to demonstrate that 2 electrons may have 3 same quantum number, but its fourth quantum number, that is spin quantum number, must be different. So this is the incorrect arrangement because they both have the all 4 quantum numbers are same in term of principal quantum number, magnetic quantum number, azimuthal quantum number, as well as spin quantum number. So when you can see the electron in the same orbital, the electron must have the spin of opposite sign. This is also wrong. So electron in the same orbitals must have the spin of must have the electron with an opposite spin, because this is how they can create the difference. The next principle is Hund's rule. According to Hund's rule, when several orbitals of equal energy are available, then the electron prefer to occupy separate orbitals rather than getting paired in the same orbital. Now what are the degenerate orbitals? Degenerate orbitals are basically those orbitals which have the orbitals having same energy are called as degenerate orbital. Okay, now how we can determine that which orbitals have the same energy and which are the degenerate? Now if we're talking about S, that is called as azimuthal quantum number is 0. This is S. When you can influence it some magnetic field, it cannot change in the direction. Now it remain S. Now so basically in S there is single S, but when we can take p orbital and when we can give some kind of magnetic field on it, we can see it split in 3 ways. Now px, py and pz. Now there are 3 orbitals which are present in the p. Now px, py, pz, these are called as degenerate orbitals. Why degenerate orbitals? Because they have the same energy. Similarly, there is the 5 degenerate orbitals for the d, dxy, dyz, dxz, dx square minus y square, dz square. Okay? So in case of d, 5 degenerate orbitals. In case of p, there are 3 degenerate orbitals, while in case of s there is no degenerate orbitals, there is only one orbital, that is s. Now in case of f there is 7 degenerate orbitals, and this number can vary upon the upon different conditions. Now according to this rule, when several orbitals of equal energy are available, then electron prefer to occupy separate orbitals rather than getting paired in the same orbitals. This is basically explained. I will explain through certain example. If I am talking about I will give you an example of the nitrogen whose atomic number is 7, 1s2, 2s2, 2p4. Okay, no, sorry, 2p3. Okay, now these are not degenerate orbitals, but you can write it like this, but the p having same quantum number have 3 degenerate orbital, that is 2px, 2py, 2pz. This is 1s, this is 2s. These are not degenerate, so you can first complete them. Okay, now these are 2p3. You cannot write them like this. This is a wrong way. According to the Hund's rule, when orbitals of equal energy are available, these three orbitals have equal energy. Okay, why? Because they are degenerate orbitals. So electron prefer to occupy separate orbital rather than getting paired in the same orbital. So instead of this arrangement, what electrons can do? Electrons can basically try to reside in a separate orbital like this. This is the correct configuration for the nitrogen. So these three have the same energy, so they can these three orbital have the same energy. Same energy mean they are the degenerate orbitals. When they are degenerate orbitals, then the electrons can basically try to reside as a single instead of pairing. Okay, so electron is first filled as single in degenerate orbitals, then pairing of electrons can take place. For example, if I'm talking about oxygen, whose atomic number is 1s2, 2s2, 2p4. Okay, 1s2, 2s2, because they have the different principal quantum number, they are not degenerate orbital. P3 degenerate orbitals, so they can firstly filled as a single, then the pairing can start. So this is basically the Hund's rule, which explains that electron in the degenerate orbitals always try to resist as a single, but they can only got pairing when all the degenerate orbitals are filled first. Here you can see the different example. Here you can see this is 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6. 6, that means this is the carbon. 1s2, 2s2, 2p, 2. So this is the correct arrangement, singly filled. This is also correct arrangement. Here you can see this is the single arrangement. Okay, now the electron, basically if they are the electron which are going to fill have the सेम डायरेक्शन ना. अगर वो डिजेनरेट ऑर्बिटल में इस डायरेक्शन में जा रहा है तो दूसरे में भी वो इस डायरेक्शन में जाएगा. अगर वो इसमें इस तरह जा रहा है दूसरे में वो यूं जाएगा तो दैट इज टोटली रॉन्ग. बेसिकली दो जो ऑर्बिटल्स हैं दे कैन गो इट इन द सेम वे. अब यहाँ पे देखें दोनों अपवर्ड है, इट्स करेक्ट. ये दोनों डाउनवर्ड है, इट्स ऑल्सो करेक्ट. बट यहाँ पे ये ऊपर अपवर्ड स्पिन के साथ जा रहा है और ये डाउनवर्ड स्पिन के साथ जा रहा है, दैट इज ऑल्सो रॉन्ग. और इसी तरह वो डीजेनरेट ऑर्बिटल, ये तीनों ऑर्बिटल जो है वो डीजेनरेट है, लेकिन हम यहाँ पे देख रहे हैं कि यहाँ पे वो डीजेनरेट ऑर्बिटल के होते हुए भी वो उसके ऊपर नहीं जा रहा, वो एक ही जगह पे गैदर्ड हो गया. दैट इज ऑल्सो रॉन्ग. सो बेसिकली Hund's rule, according to Hund's rule, electrons can basically electron can basically reside as a single when the degenerate orbitals are available. Okay, that's it for today. Thank you so much.
Please like, share and subscribe. Don't forget to press the bell icon to stay updated with our latest videos.